So in this video, we're going to see an operating system 2 marks question from GATE 2016 paper, and it is based on the topic of CPU scheduling. So the question reads, consider an arbitrary set of CPU bound processes with an unequal CPU burst lengths which are submitted at the same time to a computer system. So this tells us a lot of information. Let's note it down. So first it tells that consider an arbitrary set of CPU bound processes. So let's randomly consider three processes, P1, P2 and P3. So these are the arbitrary set of CPU bound processes with an unequal CPU burst lengths. Okay, unequal CPU burst lengths. So let me make a note of that. They have an unequal CPU burst lengths. So CPU burst is unequal. So let me just write randomly 5, 10, 15. They have unequal CPU burst lengths. And next it says that they are submitted at the same time to a computer system. Okay, so arrival time is same. Let me just make it a bit better. Okay, so this is my CPU burst, and then the arrival is same for all of them. So arrival time, they're all submitted at the same time, so 0 0 0. Now the question reads, which one of the following processes scheduling algorithms would minimize the average waiting time in the ready queue? So we are given four options, A, B, C, D, and we have to find out which one of them is going to give us the minimum average waiting time. Okay, and this is what we have noted down from the question. Now first of all, let's quickly see what is the waiting time of a process. So waiting time is nothing but the summation of time spent by the process in the ready queue. So whenever the process is not the CPU, that time, all that time, summation of all those times gives us the waiting time of every process. So let me go ahead and make a column here, which will be the waiting time of every process for all the four options that we are going to try. So let me just make it like this. Okay, so let's scroll down a bit, and I think I can zoom in now. Okay, so let's start with our option A, which is shortest remaining time first. So here is my ready queue. Let this be my ready queue, and here is my CPU running timeline. Okay, so A is shortest remaining time first. So this is the arrival time. So at arrival time 0, all the three processes P1, P2, P3 have arrived. So they will come into my ready queue. So in ready queue I have P1, I have P2, I have P3 at time equal to 0. Now we are going to implement shortest remaining time first. So if you look at their time CPU burst, this one is the shortest, P1. So that gets picked up at the CPU. So at 0 we have P1 which gets picked up, and P1 runs for 5 seconds, so it will run from 0 to 5, and then P1 goes out of the system. Now next we have P2 and P3. From P2 and P3 we have to select one. We have to select the shortest remaining time first. So P2 gets selected. So P2 goes out of ready queue. It is picked up for the CPU running, and it will run for its time period of 10 seconds. It has a CPU burst of 10 seconds. So from 5 to 15, and then P2 also goes out of the system. And then next we have P3, only one process remaining in the ready queue. So it gets picked up from the ready queue, and this is where it comes to run with the CPU. Now it has the CPU burst length of 15 seconds. So it will run from 15 to 15, that is till 30. And then P3 also terminates. So thus this is the CPU running time for all three processes P1, P2, P3. Now using this, we can calculate the waiting time of every process. Again, to revise, what is the waiting time? It is the time spent by the process in the ready queue. Now if you focus on process P1, it arrived at time 0 and it got the CPU at time 0. It means it did not wait in the ready queue at all. So for P1, waiting time is 0. Now if you focus on P2, process P2, it came at time 0. However, it got the CPU at time 5. So its waiting time becomes 5. So this is 5, And similarly, if you focus on P3, it also arrived at time 0. It was in the ready queue at time 0. However, from 0 to 15, it was just waiting, and it got the CPU at 15 seconds. So it was waiting for 15 time units. Let's calculate the average of this. This becomes 20 divided by 3, which is equal to 6.66. So 6.66 is the average waiting time for the first option, which is shortest remaining job first. So I've noted that down. Now we'll go for the next option. Before that, let's clear up this so that we can use this as a rough work. Let's clear this waiting time column. Let's also clear this. Okay. Now the next option we have is option B. It's a round robin with the time quantum less than the shortest CPU burst. Now what is the shortest CPU burst? It's 5 seconds, which means we have to take a RR algorithm which will be less than 5 seconds. So we have to take a RR algorithm with the time quantum less than 5 seconds. So basically it can be 1, 2, 3 or 4. Let's go with 4. We'll take the highest among the possible options. From 1, 2, 3, 4, we'll take the highest, which is 4. Now with RR time quantum 4, let's see how the processes will run. So again, at the arrival time 0, all 3 processes are in the ready queue. So let me make a note of it. So all 3 of them, P1, P2, P3, they come into the ready queue. Let's zoom in here. Now everyone starts with a time quantum of 0. Okay, so 0, and everyone has a time quantum of 4 seconds. So P1 runs for 4 seconds from 0 to 4. Next, P1 gets, so we have to make a note of, let me strike this out. P1 runs for 4 seconds, so 1 second is remaining. Next, P2 gets into the queue. So P2, it runs for 4 seconds, 4 to 8. So 4 seconds are gone, 6 are remaining. Next, we schedule P3. Since this is round robin, we have to go from P1 to P2 to P3, then P1 to P2 to P3. In this way, we have to do a round robin. So P3 runs for 4 seconds, that is till 12. And so we have 11 remaining. Now again, we come to P1. Now P1, only 1 second is remaining. So it will run only for 1 second, 12 to 13. And this is where P1 goes out of the system. It terminates. Next, so P1 is out. Next comes P2. So P2, 6 seconds are remaining. So it will run for 4 seconds, 13 to 17. P2 will run and 4 seconds are gone. So only 2 seconds are remaining. Next, let's go this way. Next, again P3 gets scheduled. 11 seconds were pending. Out of 11, 4 gone. So 7 are remaining. So 17 plus 4, that's 21. Now again we come to P2. In P2, now only 2 seconds are remaining. So this is P2 for only 2 seconds, which is 23. Okay, and now P2 is also out of the system. Now we have only P3 remaining, 7 seconds. So I'll just continue here down. Okay, so from 23 it will run for 4 seconds, which is 27. P3 will run, and then after 7, 4 gone, so 3 remaining, and then from 27 to 30 again we have P3 running. So in this way, and then P3 will go out of the system. Yes, so in this way, if we take a time quantum of 4 seconds, if we take a round robin time quantum of 4 seconds, this will be the CPU running time. It's called Gantt chart. Now let's calculate the waiting time. As we can see, P1 arrived at 0. So P1 arrived at 0. 0 to 4 it was with CPU, but 4 to 8 and 8 to 12 it was waiting into the ready queue, and then again it got CPU here. So the time spent, okay, the summation of time spent by the processes in the ready queue. So P1 was spending 4 plus 4, 8 seconds in the ready queue. So I'm going to write it down here, 8 seconds for P1. Now similarly we have to calculate for P2. So P2, 4. So we have to calculate the time when P2 was in the ready queue. It was not with CPU. So 4 plus 4, 8. This is 9. Okay. 4. That is 9 plus 4, 13. Skip this. And oh, it got converted. So 9 plus 4, 13. So 13 seconds P2 was in the ready queue. And similarly we go for P3. P3 also arrived at 0. And then this 4 plus 4, 8. 8 plus 1, 9. 9 plus 4, 13. 13 plus 2, that is 15. Yes, 15. And then P3. So 15 seconds P3 was waiting in the ready queue. So now we find the average of the waiting time. So how much is it? 15 and 13 is 28. 28 and 8 is 36. 36 divided by 3, that is equal to 12. So the average waiting time, now let's focus here. The average waiting time for round robin with time quantum 4 is coming to be 12. Let me make a note of it. It's coming to be 12. So this will be 12.00. Now, if we take time quantum less than 4, okay, because they have said that time quantum should be less than the shortest CPU burst. So we took 4, but if you go for time quantum less than 4, which could be either 1 or 2 or 3, you are in fact going to get a very high waiting time, because all of these processes will run for a very short period of time. So it will be P1 for 3 seconds, P2 for 3 seconds, P3 for 3 seconds, and then this will keep on running. The algorithm will keep on running for an even greater time. It will terminate after the 30th second. Thus, if you go for any other time quantums 1, 2 and 3, this is in fact going to increase. So we're going to skip that activity, and we are going to just be okay with the 4 as a round robin time quantum. Now, before we move to next, let's clean this mess. This is all not required now for the next run. Okay, so we are done with option A and option B. Now option C and option D remains. Let me zoom in and clear this too. So let me just rewrite it. It was 5, 10 and 15. Yes. Now next is option C, which says uniform random. Now what that means is the CPU will schedule P1, P2, P3 just like round robin. It will schedule P1, P2, P3 randomly. So in round robin we go line wise. We go to P1, then we go to P2, then we go to P3. However, in option C, it will randomly pick P1, then P3, then P2, then P3, then again P1, then again P2. It will randomly pick these processes with some time quantum. So again, the time quantum could be 2, that time quantum could be 4, that time quantum could be 6. Now as you can see, as you can guess intuitively, that for this algorithm, uniform random, the average waiting time could be less or it could not be less. So we can get an average time of 7, we can get an average time of 5, we can get an average time of even 10. So it really depends upon luck factor, how the CPU randomly picks out which process and how much is the time quantum that is decided. So option C, uniform random, is a very luck based algorithm. It might give you less than 6.6, it might give you more than 12.2, 12.00, it might give you anything in between of these two. So option C definitely goes out of our possible answer. Now let's focus on option D. Option D says highest priority first with priority proportional to CPU burst length. So priority is proportional to CPU burst length. So what is our CPU burst length? Let's focus on CPU burst length. Before that, let me clear this stuff. Okay, so this is our CPU burst length, and it says that our priority is proportional to CPU burst length, which means greater the CPU burst length, higher the priority. So this is going to be high because it's proportional to CPU burst length, and this is going to be low, and this is going to be, let me write as medium. Okay, so this is the priority of these three processes: low, medium and high. So when we are running option D, we are basically going to do a priority based scheduling. So in priority based scheduling, what is going to happen is we're going to start with the high priority process, which is P3. So again, as usual, in the ready queue, all three processes come: P2, P2, P3, P1, P2, P3, because they have an arrival time of same 0, 0, 0. However, the first process that will be picked up is the one with the highest priority. And why P3 is having highest priority? Because it is having the highest CPU burst. And the option says highest priority first with priority proportional to CPU burst length. So P3 gets picked up at the 0th second. So this is my 0, and P3 gets picked up, and P3 will run for its CPU burst time, so 15 seconds it will run. And then we go for the next priority, which is P2. It runs for 10 seconds, so 15 plus 10, 25. And then the next priority is P1, which runs for 5 seconds, so it's 30. So this is how the processes will be run for option D. Now let's calculate the waiting time. Now if you focus on the waiting time, P1 arrives at 0, however it gets CPU at 25. So 0 to 25, this entire time length P1 was waiting in the ready queue, so that becomes its waiting time, which is 25. Now if you focus on P2, P2 also arrived at 0th second, however P2 got the CPU at 15th second, so 0 to 15 P2 was also waiting, so that becomes its waiting time. And P3, if you focus, P3 arrived at 0, but P3 got the CPU at 0, so its waiting time becomes 0. So again, the summation is equal to 40 divided by 3, average waiting time becomes 13 3s are 39, so 13.33 becomes the average waiting time. Let us note it down here. So this becomes 13.33. So as we can clearly see, let me clear this off for, okay, let me write it in a better way. Yes, 13.33. So if you clearly focus on the options, we want to minimize the average waiting time. So the minimum average waiting time is from option A.